Okay.
Okay.
Okay, so welcome everybody to our webinar. Today we have the pleasure to hear Nicola Piana, Agostinetti, who is associated professor from the University of Milano Bicocca in Italy, and is going to talk about the full 4D passive seismic tomography for monitoring hydrofracturing operations in mines. So, Nicola, the floor is yours, and you have about 45 minutes, and then we can have some time for discussion. I just remember that the webinar is recorded, and then you can find in our website, in the webinars website, all the recordings of our talks. Okay, please, Nicola, and welcome.
Good afternoon to everybody. So first of all, I thank Sapka and Alex for inviting me to present our results from our projects, and I thank you for coming in this webinar. So today I will speak about full 4D passive seismic tomography as an application for monitoring hydrofracturing operation, and I will illustrate a few cases from Kiruna mine. This work has been done by me and Cristina Danner, Marta Arcangeli, and Sapka Dineva in the last 2 years. So the talk outline, we will talk a bit about which were the hydrofracturing operation in Kiruna and the scientific questions of our project. I will illustrate briefly the principle of a full 4D seismic tomography, and then we will see how full 4D seismic tomography can give us insight into hydrofracturing in Block 34 of Kiruna mine. Then we will analyze in detail the signature of a hydrofracturing operation on the P-wave velocity model, the fluctuation of P-wave velocity model during hydrofracturing operation, and the role of geological structure on the P-wave velocity variation. We will draw together some preliminary conclusion. And if we have time, I will illustrate a bit more some application of the fast full 4D tomography. So let's start talking about hydrofracturing in Kiruna mines. So LKB is a mining company that operates in northern Sweden and it has three main mining sites and few logistic operational sites in the north of Sweden. As we go down mining at greater depth, we know that the stress increase, and at some point, failure and rock bursting start to occur at some, depending on the site or at certain depth, and that situation is always get worse and worse, and we go down. Sublevel caving is a top-down method that implies additional induces stresses. So what was the purpose of hydrofracturing in Kiruna? So the mine managers decided that the number of large events that were occurring in the mine were too high, and so that they decided to try hydrofracturing operation as a mitigation method for reducing the number of these like big events of magnitude 1.7 events, based on some results that have been collected by Codelco in El Teniente mine in Chile. So the goal was to make this method as a system in reducing this number of magnitude 1.7 events. So they started trying hydrofracturing in Kiruna mine in Block 34. The Block 34 is, so Kiruna is a very wide and so it's a large mine. It's long as, so the operational area is about 4 kilometers. And we are talking about Block 34, where there are different geological structures that has been mapped in the past in the area. For monitoring the hydrofracturing operation in Block 34, the local seismic system has been densified by 8 sensors for So to be able to catch the seismic response of the hydrofracturing operation in more details. In light fracturing in block 34, so occurring on 28 holes, the volume injected was 15 cubic meter for the holes that were far away from the infrastructure, and the one that were closer was a bit smaller. It was like 1/3, 6.5 meters. The hole has been drilled, the hydrofracturing hole has been drilled both upwards and downwards. So here we are going to present the result for 3 holes. We monitor all the 28 holes, but we are presenting here in detail the result for 3 holes. The hole 7 that was drilled in the corner where the structure FZ26 and FZ27 25 were almost depicting a corner. The holes 12 and the holes 20 that you can see in the plots on the right. The hole 20 was the hole that was going upwards, while the 12 and the 7 was going downwards. And all the holes were drilled from level 1160 almost. So here I show you what we consider a seismic response to hydrofracturing for hole 07. So this was a downward injection from bottom up. We collected 10,000 events, hydrofracturing events, and we call hydrofracturing event where all the events that occurring in the hydrofracturing cylinder, so a region around the hole during the injection, not before and not after. So all these hydrofracturing events has been recorded, and they produced about 150,000 seismic phases. And the injection lasted for 4 days with 19 injection episodes, and the maximum magnitude that they obtained is 1.3. So, which are the scientific questions behind our projects? So, our project was aimed to answer the following question. So, the first is there is any signature, both transient and permanent, in the hydrofracturing operation in the rock mass? And if its signature is visible through tomography. And in this case, if this is the case, so if we can see something, which are the temporal and spatial distribution of such anomalies? And is there any relation between the anomaly, the P wave or S wave anomaly, and the geological structure that we have? So here, I give you a bit of detail of the project data. So we were investigating a volume that was almost 1 kilometer by 800 meter by 800 meter. And we investigated period that was almost 2 years. We have the elastic grid for the computing the tomography with a block of 40-meter grid spacing. And we observed and we used data for almost 1 million of events with 9 million of seismic phases recorded. Okay, let's give you a bit of details about full 4D seismic tomography. So I'm not going into many details of tomography because we already had webinar on seismic tomography in Mainz. Very, very, very nice talk I remember from Eric Westman. And so I will only highlight which are the difference between standard tomography and the full 4D seismic tomography. So tomography is a great tool for imaging subsurface, giving a 3D spatial distribution of seismic velocity in the rock mass, as we have seen also in Eric Westman webinar. But the mines are dynamic volume. So the 3D seismic velocity distribution is likely has a long-term change given by the exploitation. So we are removing rocks, and so we are altering the rocks, and on the long period that has been should induce some velocity change in the velocity distribution in the rock mass. Overposed to this, there are several processes that can generate transients, so short-term changes in this 3D seismic velocity distribution, like stress redistribution after blasting, hydrofracturing, as we will see, or pulse activation, and other processes. So we need to adapt 3D travel time tomography to time. So basically, the standard travel time tomography is not going to work in time in mine environments. There are two ways of computing tomography in time. The most common way is time-lapse tomography. So it means repeating 3D tomography for different time windows. So maybe consecutive time windows. But this has some problem because the length of the time windows should be linked to the investigated phenomena. So if you have a phenomenon that is shorter than your time window, you will smooth it out in the model and you will not see that. And so the user definition of the time window can bias the results. So if you have the wrong time window, so you start and end the time window is in the wrong moments, you can bias the result. So this is why we moved forward with a full 4D seismic tomography. So full 4D seismic tomography is continuous. It's creating a continuous model in time. So there is no time slicing given by the user. So you have just one model that is going through all the time and all the space. We use travel time tomography, which is the classic tomography. Then there are other seismic tomography, as you probably know. But we use travel time tomography because arrival times of the event, of the seismic event induced in the mine, are already collected by the mining company. So we don't need that additional cost for producing the data. You just get the data from the mining company, and we can use them with the tomography. And our approach is called reversible jump Markov chain Monte Carlo sampling. Let's see what it means. So is the reversible jump Markov chain Monte Carlo method is searching the parameter space for promising model. The models are represented as an ensemble of adaptive 4D Voronoi cells. Both the number and the shape of the Voronoi cells adapt to the data, both in space and time. The full suite of model composing the Markov chain is used to compute posterior probability distribution of the investigated parameter. So we have at the very end, we have for each point of the mine, we have a value that is representative of a velocity, seismic velocity in that point of the mine in time. Even the fact that we have posterior probability distribution, which is a statistical indicator of how the parameters are resolved, we can use Bhattacharya distance to understand better if the parameters are changing in time. Okay, let's see a bit about hydrofracturing in block 34 as seen by our algorithm. So I just show you this slide to illustrate how I present the results of our tomography. So this is on the colored panel is a posterior probability distribution on a map XY of the p-wave velocity at a certain time. Okay, so the colors are representing the velocity. Red is high velocity and blue is low velocity. And I also added some more details like the fault fault zone, so the violet circle is the hydrofracturing hole that is active at that time. There is also the ore body and the seismic station. And also I'm presenting the seismicity in the other plot on the lower left, where you have the blast, the seismic events as red dots, and the circles are the hydrofracturing holes. The triangles is the seismic system. This is not enough, so sorry for the complexity of the presentation of the results, but we also have a VPVS ratio, as you see in the second color panel. And we have those gray panels on the left, on the right, sorry, are representing the Bhattacharya distance. So this is how we can evaluate if our results are robust or not. Where you see a black area in those gray plots, those black areas indicate a robust change in time of the seismic velocity. To have more context, I was also adding the seismicity rate on the bottom of our plot, and when the yellow bar is indicating in time when the hydrofracturing operating is starting and ending, and these red stars are the blasting sequence in the area. And how I can present that? So I have a full 4D model, but to make a movie, I cut from the model hourly 3D slides. So I'm cutting 3D slides for you from the 4D models, and I'm producing a tomographic model. So we can see the results as a movie. So let's see the first of our blocks. This is hole 7. Sorry, I have to exit the full screen presentation because the movies is not. So let's see. So it's moving. This is when it starts. Sorry, yeah, I cannot stop it in this way. So let's go here. Can you still see the presentation? It's okay. No.
Yes.
Okay. So I operate the movies from here because it's easier. So if we start, we can run the movies. Here is the hydrofraction is starting, and then at the end, when here the operation is ongoing, and then is exiting, and we have no more anomaly. So if we play the movies a couple of times, we can see the tail. So when the hydrofraction is starting, we have this red anomaly. It means a high velocity anomaly where the hydrofraction in hole is operating, like here, you see. And then when you have at this time it's 18 in the afternoon, sorry, it's 7 p.m. because this is UTC time. The operation is halted because the shift because of the war shift, and the anomaly is decreasing. Then it's increasing again in the morning, the day after when they started again doing the hydrofracturing, and it's decreasing again during the night. And then in the third morning, they started again in injecting. You have again the high P wave velocity anomaly in the borehole, in the hydrofracturing hole area. And then it's decreasing at the end of. So this is the night again. This is interesting. The anomaly is fading, but it's not totally disappearing, and then it's increasing again the morning where they were doing hydrofracturing. And this is a classical signature of the hydrofracturing in the mine. So when they inject water, as they start injecting water, they had this high P wave velocity anomaly arriving. And this is very well, so I would say that this is quite well constrained in the model. You see is black here in these two circles. It means the Bhattacharya distance is quite high, which means that those changes are statistically consistent with the data. And then when you have black again, you have the increase and the decrease related to the opening and to the closing of the dry fracturing activities. So this is quite clear in many, so this is one of the clearest example, but it's clear in many of these hydrofracturing operations that we monitor in Kiruna. But this is not always the case, so I want to show you more examples. So we have example from from hole 12. where we have a slightly different pattern. So we can go here and play the movies. And if you see here, you have less intensity in there. So not all those operation gave us the same intensity in the VP anomaly. So it's arriving here at the beginning. And if you see, the anomaly is kind of parallel here to the proposed fault zone, and then is decreasing, and then it's going to disappear. So not always we had uh, um, the same results. In particular, if we go for a block for a hole 20, which is this one, we can see that in this case, and I have to remember that hole 20 was drilled upwards, we have almost no seismic response, no events, and almost no anomaly appearing. So in some cases, they had no seismic response, so no events created in the hydrofracturing hole, and they had no size, so no anomaly in our model arriving. So if we want, we can play these movies later. Again, I want to go a bit further with the presentation, but I will be happy to play these movies again with you if you are interested in more details. So if I go sorry, this is the second and this one. So which is the signature of this hydrofracturing operation in P-wave velocity model that we saw in our experiment? So basically, we have an increase in VP velocity up to 10% during the hydrofracturing. But the amplitude of this anomaly is related to the location of the mine. As I show you in two cases, in one case is a sharp and intense anomaly. In other cases, is less is not that intense. And the amplitude is related to the whole direction. So when we were looking to upward hydrofracturing hole, we had mostly no VP anomaly in the model. Growing from the hole toward outside and disappearing from outside toward the hole. So if we look in detail this operation, the anomaly is going from the hole. When it's start the injection, the anomaly is going from the hole outside, and when the injection is halted, it's coming from outside and decreasing to inside to the hydrofracturing hole. So basically, our answer is yes. Is there any signature? Yes, there is signature in the velocity model, and it's visible through seismic tomography. And in some cases, depending on the whole location. So if we look to the spatial extension of this anomaly, so the anomaly is always going toward a bit like 100 meters from the hydrofracturing hole. We have to remember that our resolution here is 40 meters. So basically is well above our our minimal resolvable volume. So it's definitely larger than 40 meters in all the cases where it was observed. And this spatial extension is consistent with the activated rock mass volume. That is how they call it in hydrofracturing operation. This is the convex volume around all the activating joints during the hydrofracturing modeling. You can check this paper by Anderson 24. How long it extends in time. So this plot show you the BP velocity at the center of the hole and in orange, and in the Bhattacharya distance in light blue. And this is a time series showing all the days, so the before and after the hydrofracturing. So the hydrofracturing moment is a gray area. So the hydrofracturing is starting in where during the different days where you have the red bars, and it is ending at the day during the with the blue line, the vertical lines at that time. We define start and end with the presence of the seismic events, okay, in the hydrofracturing cylinder. So if you look, the velocity is rising sharply at the beginning of the injection, so when the injection starts, but it's usually decaying, so the bhattacharya is shifted at the end of the phase, or the fracturing phase. So this means that the anomaly is lasting more. So it's appearing almost immediately when the injections start, but is lasting few hours after the injection. And this is a pattern that has been seen in many hydrofracturing holes. So let's talk a bit about the roles of the geological structure in confine. So in the interaction of the BP anomaly with the geological structures. So we are talking about block 34 in Kiruna mine, and there are many different structures crossing the hydrofracturing operational zone. And structure have different trends. So mainly we have two fault zone 25 and fault zone 26, and a proposed structure that is running almost parallel, I would say, in this plot to fault zone 25. So if we look to the anomaly in a map view and in a vertical profile view, for example, for hole 20, it's hole 7, we see that the anomaly is confined in both in the map and the vertical plane from the fault zone 26 and fault zone 25, and from the mined volume at the top. So it's not going through the mined volume. If we look to hole 12, again, we have that the P wave anomaly is confined by the fault zone 26, the ore body, and the mined volume. So the geological structure play a role in confining the anomaly in a certain portion of the mine. So if we have a look to a close-up on the stress and seismicity, and we see again hole 7, and I give you a warning. Unfortunately, I forgot I have the reverse scale. So blue now is high P wave velocity anomaly. We were thinking if there any link between the P wave velocity anomaly that we see and the induced seismicity, sorry. And so we look here at the movie for hole 7, downward injection close to the fault zone 25 and 26 on a vertical profile almost normal to fault zone 26. Sorry, I exit the full screen presentation to play the movies again. Is this one? So if we play the movie and we see here we see the anomaly is developing, and all the seismicity is going within the blue zone, which is, sorry, is reversed from the previous slides, is the high P wave velocity anomaly. And this is basically all the phases are the same. You see here, if you see here, you have the anomaly and all the events are occurring inside the anomaly. So basically, we can play this later again if you are if you are interested in many details. I can zoom in more detail. But if we want to discuss this, okay, again, this is the movies and all the events occurring within the blue zone, which is here the high P wave velocity anomaly. So the induced seismicity is strictly developed within the P wave anomaly, as you see from this picture and that you've seen from the from the movies. It starts developing few hours after the P wave anomaly. So the anomaly starts first, and then the seismicity starts. So increase. If seismicity indicate localized stress increase, we think so. This is possible that P wave variation should be a proxy of the stress increase. So if we relate the seismicity to stress and seismicity to P wave velocity anomaly, so that P wave velocity increase, it means increase of the stress, local increase of the stress. So to conclude, hydrofracturing affect the rock mass inducing a transient P-wave velocity increase up to 10%, which can be revealed using passive seismic tomography. The special extension of this transient P-wave velocity anomaly is within 100 meters from the hydrofracturing holes. But it is a limit. It depends on the location of the hole in the. So I think 100 meters is almost the maximum. Then it depends on the location of the hole in the mine. So P-wave velocity anomaly is detectable in the very first hour of the operation, and then it lasts few hours, about 3 hours after the shutdown of the hydrofracturing operation. And we saw with the hydrofracturing hole 7 that the repeated operation can introduce a longer decrease in time. So at some point, when they were repeating the hydrofracturing operation in the same hole for more days, the anomaly was not fully decreasing during the night, but was still there. And then it was only disappearing at the very, very end of the hydrofracturing, of the last hydrofracturing operation. So the geological structure plays a role in the spatial confinement of the anomaly, as we see the mined out volume, the fault zone, and also we were also able to correlate our anomaly with a proposed structure that was not already mapped in the mine, but was proposed by the geologists. So this is for the conclusion of my analysis of the full 4D seismic tomography related to hydrofracturing operation. And I think we have time. I give you some insight how we use also this tomography. So it could be interesting for you to discuss, for us to discuss more application. So if our target is building long-term variation of seismic velocity in rock volumes in the mines, and this is another project we had with LKB, the algorithm can be applied to a longer period. So you can compute, this is a series of 7 years of data, and you can map the velocity over these 7 years in Kiruna. And from this, you can compute a P-wave velocity time series in particular point of the mine that you are interested. And so you can make time series that can be combined with other observation. In this case, we were looking to the cumulative number of seismic events in the area. And you can make some kind of interpretation of the results. So you can use this tomography to make time series of P-wave velocity and S-wave velocity in specific points of the rock volume that you want to investigate. If the target is reconstructing geological structure, for example, you can apply our algorithm to full resolution model. So it's more than 40 meters. So the shed were reduced so to have a better geometrical resolution. For example, here we show the mined out volume from the LKB data on the top, and how our model compare with this mined out volume. So we cut a vertical profile in the mine, and we see that the mined out volume is clearly limiting our P-wave velocity anomaly. And finally, I want to show you how to navigate the model, because sometimes I have to stop sharing because I need to go on my um, on my web browser. So I stop sharing this one and I share with you this other model. So this is a system that we so it's a way to look inside the model. So our model is a three-dimensional model, full three-dimensional model in time. So you can change the model in time. You can go and pick one a place and you see this is the time history of that place. So you can zoom in. The bars are related to the uncertainty because our model is a probabilistic model and you have the uncertainty for each block. You can change the threshold and just look only to the very, very well defined, so the well resolved portion of your rock mass. You can slice the surface and see one, for example, this is Z slice at 1080 meter in Kiruna. So you can navigate our model. So those models are really 3D and can be navigated in time. Our original model is fully 4D, but this has been done for the operator in the mine. It's easier for operator to look inside the model and pick a portion of their rock volume and check what is going on there. So I share again my presentation if we need to go back. And so I thank you to be here today, and I'm open to questions. I think we have, I'm staying in 40 minutes, so it's okay.